currently recording this, so if you have any problem, you can let me know. So if there's no problem, we are going to start. And I share the questions with you. Now we are going to start with the first exercise, functional and complex analysis. So today we are going to work on functional and complex analysis. So this subject is what we did on the 23rd of June 2026. So the duration was 1 hour, maybe 150 minutes. So what we are going to do here is to try to solve it and to explain maybe some different concept that you have seen during the lecture, and maybe you can adapt it in the way that you have seen it with your lecturer, because I'm going to do it in my own way. But if the lecturer mentions something particular, you can let me know. So exercise 1. Exercise 1, we have the space C 01, so which is the space of continuous functions from 01 to R. So this is the meaning of this. Someone can trace here too, so we can put 0 here. So it is the same thing. So 0 here means that the degree of differentiability is 0. So the order of differentiability is 0. So it is the same thing. So we equipped with the supremum norm, as you know. This is what we call the supremum norm. So which is the supremum of the absolute value of x in 0, 1. By the way, 0, 1 is a compact domain and the function f is continuous. So this one can be also written like the maximum of this. So the supremum and the maximum, they are the same. So you can check it by look at the Bose-Novo's theorem. But it is not important here. So the first question is to state the Arzela Ascoli theorem. So let us state the Arzela Ascoli. So I know that you know, but it is always good to state it. We used to say in French that repetition is the mother of science. Now, if you have a KD like this, a compact metric space, so it is good for you to know what is a definition of a metric space. what is the definition of a compact matrix space. So maybe we cannot give it here, so you can just go through the notebook, but it's not, I think that it's not very important to mention it here, but it will be good if you know it. At least a matrix space, as you can see, it is this coupled why K is an non-empty set, G is a metric on K, and you know the definition of a metric. Now, if you have this, let F like this, calligraphic F, included in CK. So this one is like a family, so a family function. Then F is compact in CK equipped with the supremum norm if and only if F is closed, bounded, and equicontinuous. Yeah, I think I know that maybe there are people in German, there's, yeah, it's not maybe the same thing. Why? Because when you have Kg, a compact matrix space, you have F, a family of continuous function in zero in K. Now, this F, another version of the Arzela Ascoli Theorem is F is pre-compact in CK equipped with the infinite norm if and only if F is bounded and equicontinuous. So it means that if you remove the closeness, this F will become pre-compact. So if you want to write that F is pre-compact, you have to remove close. So maybe I can put it down here, the same thing, but I'm going to remove compact. So but I'm going to substitute compact by pre-compact, and I'm going to remove close. Be a compact matrix space. Let F then the family F is pre-compact in CK if and only if F is bounded and equicontinuous. Now, you know what means to be bounded. So it means that if you take any element in F, so any function in F, you have just to show that the norm is finite. So the norm is finite. Equicontinuous. I'm going to give maybe the definition of equicontinuous for you. But the theorem is up here, so just the four lines. So you can decide to choose what is written in blue or what is written in green. But this one is not necessary, but I'm just going to just like a comment. So a family of function f, it's a to be equicontinuous if for Lxy in X. So normally I was supposed to define X or Y. So I was supposed to define two metric spaces before saying this, but I'm going to give it after this definition. So you assume that before starting this, we define two metric spaces, X dx, Y dy. So f is said to be equicontinuous if for all X and Y in X and for all epsilon there exists a positive delta such that if the distance between X and Y is less than delta, then the distance between f of X and f of Y is less than epsilon for all functions that we take in the set, so in the family of functions f. So, and to make this definition, so I'm going to put here x dx, y dy, two matrix spaces and what else? A family of functions. Okay. As I said, the theorem is just what is written in blue or what is written in green. Now, what is the first question? The second question. So let us check if the following family of continuous functions is pre-compact. According to you, what are we going to do? Or which theorem do we need to use? What is the theorem that we should use? So the first question was there to give you the idea on about how to solve the second question. So the first question gives you the idea to how to solve this question. So you see that in the second question, they ask you to prove that you have a family of functions which is pre-compact. And the first question is about the Arzela Ascoli theorem. And the Arzela Ascoli theorem is there to prove that a family of functions is precompact or compact. So you can see that we are going to use what is written in green here. So the only thing that we have to show is that we have to show that that family of functions is bounded and equicontinuous. So if we show that the family of function, that family of function is bounded and equicontinuous, then we will conclude that the family of function is precompact. So that is what you should do. So if you don't even know that it is what you have or you need to do, that is the problem. The problem sometimes is that they ask you a question, but you don't know what to do. So what we have to do here is to show that the family of functions of continuous function is bounded and equicontinuous. So what is that family of functions? F is given by Mhm. So I'm going to write it like this. So you know that x is in 0, 1. So it's not useful to mention a 0. So the first thing is the boundedness. Now, this thing is very easy to see that it is bounded. What we know is that x is in 0, 1. X in 0, 1. What can you say? So obviously you can see that f is positive because x is positive, square root of n is positive, exponential is positive. So you can see that if f is positive, it means that 0 is less than f. That is what it means that f is positive. So the sequence of function fn is positive. Now, we know that nx is positive. Exponential of minus nx, it is a decreasing function and it is less than 1. So if this one is less than 1, it means that you have this one less than x over n. Another way to show the boundedness is that you can directly compute the supremum norm of fn of x. I think that you're going to get something like 0. It is finite. So then you conclude that f is bounded. Otherwise, you can try to do as I'm doing like this. So you have this. Don't forget that x is in 0, 1. So this means that x is also less than 1. Now you have 1 over square root of n. So Evans quantity is also less than 1. So if you take the supremum, you are going to have the supremum of this is less than 1. And this one is for any function in the family of functions of continuous function. So if this one is finite, then the family of function is bounded. So I hope that everything is clear here. So if it is clear, we can continue. And we have to move to the last step, which is the AQ continuity. equicontinuity. So you know the definition of equicontinuity. And another way to prove the equicontinuity is you can use the Lipschitz continuity definition or idea. So you know what means for a function to be Lipschitz continuous. So, and as we did in secondary school, here we have a function of one variable. So what we can do is just to compute the derivative of this function and to try to bound it. So take the absolute value of the derivative of this function. So if we compute, we know that f is a differentiable function. So f admits derivative. Then what is f prime n of x? So this one is just a product of two functions. You know how to differentiate the product. So it is equal to this minus this. Now this is equal to our square root of n times 1 minus nx. So if we take the modulus or the absolute value of this, what are we going to have? We are going to have, so this quantity is positive, so we don't care. So the absolute value is going to be here. Now, as you know, the absolute value of this, by using the triangle inequality, is less than this. It's no minus, it is plus, as you can see. So it means that this one is less than. So even x, okay, yeah. Now this is less than exponential Now, what you can see is that this quantity is less than 1. Since that exponential of minus x is less than 1, so we have this one less than 1 over square root of n, which is also less than 1. Now, this one is going to give us square root of n x exponential minus x. Now, I want to, the thing is that you know that when you are looking for the upper bound of this quantity, it should not depend on n and x. So what I'm going to try is to find an upper bound of this quantity that depends on n and x. So if I take, for instance, you can do it in your way, so it's not necessarily the same way, but you have to understand the main idea. So if I take t equal to nx like this, then what do we have? Square root of n x equal to what? Square root of nx exponential equal to, so if you replace this quantity by if you replace nx by tn, you're going to have here t power square root of n times exponential minus 1, and this is less than t exponential minus 1, since that 1 over square root of n is less than 1, so you just have t exponential. Now t equal to nx, n is positive, x is positive, n is positive, so it means that t is positive. So if you take the supremum of this, when t is positive, because you know that this quantity is less than the supremum of this, and this one is 1 over e. So what do we have? We have that the absolute value of f prime of fn prime of x is less than this. This is for all n and for all x in 0, 1. So when you have this, then you're going to have fn of x is less than, and you conclude that f is equicontinuous. F is equicontinuous. Now, since f is both bounded and equicontinuous, by Ascola as by Arzela Ascola or Ascoli Arzela, f is precompact. So you see how it was very easy. So the only thing was to show that the family of function is bounded and it is equicontinuous. Then when you have shown the boundedness and the equicontinuity, then you conclude that the family is precompact. Now to check that this family is compact, you have also to check that this family of function is closed. I think that it is all for the exercise 2, and we justify all our answers as the lecture asks. So I think that there is no problem. You understood everything. Nice. So we are going to move to exercise 2. So here in exercise 2, they have to give the definition of LT of the torus and its inner product. So yeah, you have to know that this one is the torus. So people who will be doing geometry, they will understand very well this notion of torus. So it's what we call a manifold. Now, this is also written like this. So people who are doing pure algebra, I can understand this quotient space. Now, so you have to understand that L2 of the torus is isomorphic to L2 of this. So we can define L2 of the torus by defining L2 of 0, 2 pi. So if it is very difficult to work in L2 of the type of the torus, you can work on L2 of 0 or 0, 2 pi. Now to give them proper definition of this. So this is the set of functions from to C, measurable, such that the integral over a torus of the modulus of h squared is finite. So it is easy to define the inner product here. Since that the norm, you can see that this one is the norm. So to define the inner product, so the norm of h just the integral over the torus so it means that the inner product between two elements, if I take f and j, the inner product is just the integral in the torus of fx j conjugate. So that is all. Now, basically, we are going to take this definition instead of, so we are going to take now this one. So if we identify, so let me mention this. If we identify the torus with 0, 2 pi, so with periodic function, then we have this. So instead of what we previously take, we are going to take the function from 0, 2 pi to C measurables such that the integral from 0 to 2 pi of this is finite. So you can do the same thing. So if you want to take the inner product here, it will be the same inner product. So just that you will take 0 to pi. If you want to take a norm, yeah. So these are the basic definition that you were looking for. But in our case, you notice that we are working with real for function array value. So we are working with real values. So it means that I'm going to take UV like this. So the inner product UV equal to, because we are not going to C. So we are not in C, we are in R. So I'm not going to take the conjugate. I can just take it like this to see that functions are real value. So we don't have complex value. Function, they are not complex value here. So real value. So that is why we are going to take it like this. Simple this. Now, if we take the data that was given, so the first thing is to compute the inner product between f and g. So we have to compute the first question. Just compute the inner product between fx equal to sine of 10x plus 7 cosine of 2x and gx equal to cosine of 2x. So we want to compute the inner product of this. So as you know, these are real value functions. So what we need to do is just to use this formula to compute the inner product. You just have to use this formula to compute the inner product. So I hope that this definition of inner product is the same thing that was given to you during the lecture. So the inner product between f and j is just the integral from 0 to pi of fx gx. We are not putting any conjugate on g because we don't have complex value. Now you have to replace. So when we replace in, we have sine 10x plus 7 cosine 2x times cosine of 2x dx. So if we expand this, you have to expand. This one is sine 10x times cosine 10x 2x, sorry, plus 7 cosine 2x times cosine 2x is cosine 2x squared. Now, I don't know if you did something in Hilbert spaces. Even if you didn't do that, you have to know that cosine and sine form a basis. So sine, this sine 10x cosine 10x, this one, that they are orthogonal. They are orthogonal. Maybe if you don't know this, you have to compute this by using trigonometric formula. And if you don't know, you are going to suffer. Sorry if you don't know. I don't know if you would like me to recall some trigonometric formulas, but before doing that, I would like to tell you this integral is 0. You should know this because cosine and sine, they are orthogonal with L2 in L2. Maybe I'm going to record some trigonometric formula before continuing. Now you know that I'm going to record some duplication formula. Cosine of a plus b is equal to cosine of a cosine of b minus sine of a sine of b. So I can take it like 1. Cosine of a minus b equal to cosine of A, cosine of B, plus sine of A, sine of B. Sine of A plus B equal to sine A cosine B plus sine B cosine A. Sine of A minus B equal to sine A cosine B minus sine B cosine B cosine A. We have a lot of formula. Cosine square of x plus sine square of x is equal to 1. You know it very well. I'm not going to do tangent formula here because I think that it's not useful. I know that tangent is just sine, the ratio between sine, so sine over cosine, you know it. Now, you have here sine, cosine, sine, cosine. So if you are looking for a formula with sine A, cosine B, so if you take 3 and 4, if you take maybe 3 plus 4, what are you going to have? 3 plus 4 is sine A plus B plus sine A minus B, which is equal to what? If you add 3 and 4, you are going to have 2 sine A plus B. So with this, you are going to have sine A plus B equal to half of sine A plus B plus sine A minus B. Same thing, if you want maybe a relation between cos A, cos B, or sine A, sine B. So if you need, if you take maybe 1 plus 2, 1 plus 2, you are going to have cosine A plus B plus cosine A minus B equal to 2 cosine A cosine B. So to have a relation between a cosine B, you have cosine A cosine B equal to half of cosine A plus B plus cosine A minus B. But otherwise, if you take 2 minus 1, if you take 2 minus 1, you are going to have cosine A minus B minus cosine A plus B equal to 2 sine A sine B. Then you are going to have sine A sine B equal to half of cosine A minus B minus cosine A plus B. So you are going to see that for this different formula, you can develop all the formula that you have. If maybe if here if we take the formula of, if we take 3, from 3, if A equal to B, what do you have? From 3, if A equal to B, you have sine of 2A. So you are going to have A plus A, which is equal to 2A. Here you are going to have sine A cosine A plus sine A cosine A. So you are going to have sine equal to 2 sine A cos A. If you go here, if you go from 1, if A equal to B, you have cosine A plus A. So A equal to B, you are going to have AA. So you just replace everywhere by AA. So you are going to have cosine A cosine A minus sine A, which is cosine A square minus sine A square. So you are going to have cosine 2A you are going to have cosine 2A equal to cos square A minus sine A square. I can call this one 6. I don't know if what I'm doing is useful, but let us continue. So from 5, you have cosine square plus sine A square equal to 1. So this means that sine square is equal to 1 minus cosine A. So from 6, if you replace sine A square by this, you have cosine 2A equal to cosine square minus, you replace sine by this, 1 minus cosine square. So you expand, you have 2 cosine square minus 1. So it means that you have cos square equal to 1 plus cos 2A over 2. So this one is like a linearization of cosine square. So I'm going to stop here. There is a lot of things. So I'm just going to use what is useful. So we can just take this one. Cosine A square, cosine A square equal to 1 plus cosine 2A over 2. So if you go back, if you come back here, we know that this one is already equal to 0. And if it is difficult, we can use any of this formula that we found among the Green's formula, and you compute it. So you follow all the steps, you will see that you have 0. So if you continue with the inner product, so the inner product here between F and J was just equal to this of 2x. Now, you know that we don't know the antiderivative. How to find the antiderivative of cosine square of x? So the easiest way is to linearize this thing, because we know that we can find the antiderivative of linear trigonometric functions. So when I'm talking linear, it means that we don't have those square, those powers. So the degree is 1. This one, so we take 7, you replace cosine square of 2x by this formula in green. So you are going to have 1. Our a is 2x. So if you replace a by 2x, you're going to have cosine 4x over 2 dx. So you have 7 over 2, this integral dx. Now, it is very easy for you to find the antiderivative of this. So this is just what the antiderivative of 1 is x. The antiderivative of cosine 4x is 1 over 4 sine x from 0 to 2 pi. So when you replace it by 2 pi, so you are going to have 7 pi. By 0, you are going to have 0. So this is 7 pi. This is 7 pi. So as you can see. So it is not long. That is that you should know this trigonometric formula and this property of Hilbert spaces. So that is the main problem. You can see that we can do this thing in 4 lines, but as we wanted to explain everything, that is why we decided to write it in more than 4 lines, and we also put some comment, as you can see in green here. Now we need to exhibit an orthogonal basis of the orthogonal complement of J. So in another way, we are looking for the orthogonal basis of this. Now, we want an orthogonal, basis of the orthogonal complement of J. So what is J? Don't forget that J was like cos x, 2x. So this one is going to be just the span of cosine 2x. Since that J is cosine 2x. So to do this, we are going to recall something. So recall that recall the standard orthogonal basis of this of L2 of this. So 1 cosine nx sine nx, so with n greater than 1. So as you can see, this one is the standard orthogonal basis of this. The only basics vector that is not so. The only basics vector that is not orthogonal to J equal to cosine 2x is cosine 2x itself. I hope that you understand why cosine 2x is not orthogonal to itself, because if you compute the inner product between cosine 2x and cosine 2x, so the integral from 0 to 2 pi of cosine 2x squared, you're not going to have 0. So that is why G is not orthogonal to itself. So we have to remove this basis. So we have to remove cosine 2x in the basis, because if you compute the integral between cosine 2x and you compute the inner product between cosine 2x and cosine 2x, which is the integral from 0 to 2 pi of cosine 2x times cosine 2x dx, which is the integral from 0 to 2 pi of cosine 2x squared. And you can see we previously did it. So that integral is not equal to 0. So they are not orthogonal. You also have to know what is the notion of orthogonal with. in Hilbert spaces. So it means that if you compute the inner product between two functions, you have 0. It means that the two functions that are orthogonal. No, indeed, sin nx is orthogonal to cosine 2x for all n. Cosine nx is orthogonal to cosine 2x for all n with n different to 2, as it was mentioned. 1 is orthogonal to cosine 2x. So, therefore, an orthogonal basis of the complement orthogonal of J is obtained by removing cosine 2x from the usual trigonometric basis. So, one orthogonal basis is one union sine nx union cosine nx indifferent to 2. So I think that everything is clear. Everything is done with exercise 2. So I hope that I'm not rushing. If I'm not rushing, can move directly to the next exercise without wasting time. Maybe you are tired. So exercise 3. Consider a sequence given like this. Square root of n characteristic function given like this, where so they give the definition of the characteristic function for more precision, or the indicator function as you want. So it is equal to 1 if x is in 0, 1 over n, and 0 otherwise. Now, what is the first question here? Okay, but we can give, so Fn is what finally? You just take the square root of n multiplying to this characteristic function. So 1 times square root of n Now, um, let us let us compute. Let us compute this. You know the formula, right? Ah, no. Let us compute this. So by definition, you know how to compute the edge genome of continuous function. So I will put the square here because I don't want to put the half power or the square root in the right hand side. So it is equal to this. Yeah, right? I hope that everything is clear. Oh, uh, so by definition, so how can we do this now? Okay, you know that this one is from 0 to 1, right? But how you can see how the domain is so we are going to move from 0 to 1 over n, and the remaining part, the integral, it is 0 there. Now, this one is, it is like this. So it's the integral from 0 to 1 over n of square root of n power square root of n square. So it is n here, dx. And the remaining part, it is 0. So we don't need to put this, but you can just say that this is this. So this integral, it is equal to 1, right? It's 1. So we computed the genome of the sequence Fn. So I hope that this um so this is for all n. The next question is to determine why this one. Second question. So let us determine the pointwise limit of Fn and check whether Fn converge strongly in L2. So as you know, this is very easy. So the first thing just that if you fix your x greater than 0, then for n very large or large enough, you know that 1 over n is less than x. Yeah, because when n is very large, 1 over n is 0, and 0 is less than x. We are together. So for n large enough, 1 over n is less than x. So what does it mean? It means that x does not belong to this interval. Because if 1 over n is less than x, it means that x is greater than 1 over n. So x is not in interval, it's in the interval. It means that fn of x is equal to 0 for all sufficiently and for all sufficiently large value of n. So you understand this is f. F was given like this. We see that f is equal to square root of n if x is between 0 and 1 over n. But here we notice that when we fix x positive or greater than 0, for n large enough, we notice that when n is large enough, 1 over n is less than x. So if 1 over n is less than x, it means that x is greater than 1 over n. So x doesn't belong to the interval 0, 1 over n. So if you don't belong to 0 n, 1 over n, it means that you cannot be equal to square root of n. So it means that you are equal to 0 because you are in the complementary interval of 0, 1 over n in 0, 1. So if you are not in 0, if you are not in 0, 1 over n, you are in 1 over n 1. So yeah, this is otherwise. And when you are here in otherwise, it is 0, since that you are not in 0, 1 over n. So that is what you have. So you can conclude those for every x greater than 0. The pointwise limit of this is 0. Now what happened at x equal to 0? What happened at x equal to 0? At x equal to 0, so 0 is not in this interval. 0 is not in this interval. So since 0 is not in this interval, maybe I forgot something here. Maybe it's better for me to put. So if 0 is not in this interval, so it means that 0 is down here in otherwise. So at x equal to 0, we know that this one is not in 0. We know that 0 is not in this interval, sorry. So also fn of 0 equal to 0. Therefore, what we can conclude is that fn of x tends to 0. So this one is the pointwise limit, so don't confuse. For every x in 0, 1. So the pointwise limit is 0 for every x in 0, 1. Now you have to check. The next thing is to check. Does fn converge strongly? So does fn goes to 0 strongly in L2? So the first thing you have to know what means converge strongly in S2. So strong convergence in L2 means that the norm of Fn minus 0. So if instead of 0 it was maybe F here, you will take Fn minus F. If this norm in L2, this norm in L2 norm, so this quantity in L2 gives 0. That is what it means by L2 convergence. But from part I, so what we did from part I, the norm of Fn in L2 was equal to 1. This is different to 0 for Rn. Then Fn minus 0 in L2 equal to 1, and this does not go to 0. So Fn does not converge strongly to 0 in L2. So that is the conclusion related to this. What is the next? So the next thing is to define weak convergence in L2 and determine whether Fn converge weakly in L2. Identify the weak limit if it is exists. So it's mentioned that the dominated convergence theorem may help you. Now, let us define weak convergence in L2. A sequence may be UN in L2 converge weakly to U in L2 if for every test function phi in L2, normally this phi is in the dual of L2, which is L2. We have the this goes to this. So that is all. It's not something difficult. That is just the definition of weak convergence in L2. So you see how it was very easy to see. Now that we want to check, so let us determine now let us determine whether Fn converge weakly in L2. So to do this, we now test Fn against or with an arbitrary phi in L2 of 0, 1. So that's what we are going to do. So Fn with phi, what do we have? So the integral from 0 to 1 of Fn of x phi x dx. So this is what, don't forget that, don't forget the way that our f is defined. This is our f. So we have to divide our domain into two intervals. So, but in the other interval, you know that it is 0. So we don't mind. Phi x dx. So it is equal to this. If we take the modulus or the absolute value of this quantity, and we are going also to apply the Cauchy swap. Yeah, so this one is less than this. And if you apply the Cauchy swap, you are going to have something like this. So this is what we are going to have. And what do you can notice that, so this integral is just, so this one is just this one is just 1 over n. So this integral is just 1 over n. If you put the half power, is going to be the square root of n, and you have the remaining quantity, this one. And don't forget that this one is also less than this quantity. And this is the L2 norm of this. This one is the L2 norm of phi. Now, it was mentioned that it was possible to use, we mentioned that it was possible to use what we call the dominated convergence theorem. So I don't know if I'm going to recall the definition of the dominated convergence theorem, because with the dominated convergence theorem, it mentioned that if you have a sequence of measurable functions from maybe R to R, now if you can find an upper bound which is integrable, and your function fn converge to 0, so it means that okay, let me record that. I'm going to record the limited convergence theorem, because by using the dominated convergence theorem, I can just say that by the dominated, I'm going to finish it. I'm going to finish this one. So the limit of this quantity which is equal to the limit of this quantity. So you can switch the integral with the limit. This one is because of the dominated convergence theorem. So which is what? 0 times this. So which is 0 and which is the inner product between this one and this one. So then f converge weakly to 0. So it is written like this. This is what we mean by weak convergence. So I'm going to record the dominated convergence theorem for you. Normally, I know that you know it, but I know it is useful to record that maybe it is like there is no choice. So Lebesgue dominated convergence theorem. So let Fn from Rg to R maybe taking it like this be a sequence of measurable functions. Suppose that I yes, there exists a measurable function f from Rg to minus plus infinity such that Fn converge to f almost everywhere. And you have to know that the pointwise convergence is stronger than the almost converge the almost everywhere convergence. So it means that if you converge pointwise, you converge almost everywhere. And with this exercise, Fn was converging pointwise to 0. So it means that Fn converge almost everywhere to 0. And there exists a summable or integrable function. Summable or integrable function. So it means that the function which is in L1 functions j from Rg to this such that this one is less than this. In our case, you are not going to note that you are going to notice that our g here is this quantity, this integral, so this norm. This is our g. And our sequence of function is fn. And this is our g. So that is why we can apply the dominated convergence theorem here. So this g is integrable since that it's a constant. So it is positive since it is also a norm. So you can see that g goes from r to 0 plus. So 0 plus means that g should be positive. This is for almost every x in Rg. Then the limit of the integral of fn is equal to the integral of the limit. That is all. And the limit, the integral of the limit, so the limit of fn is f. That is why it is written like this. So that is the convergence. So the Lebesgue dominated convergence theorem. So that was all related to the idea of the Lebesgue dominated convergence theorem. And the work limit is 0, as you can know. So the work limit here is 0. So we have shown that fn converges quickly to 0 in L2, but it doesn't converge. It doesn't converge strongly to 0 in L2, but weakly is possible, and also piecewise. Is there another exercise? Last exercise, a previous exercise 4. The last exercise is exercise 5. So this part is the part related to complex analysis. And the first question is a definition that you have maybe in your notebook. So exercise 4, the first question is to write the definition of isolated singularities and the definition of J classification. So I don't know how you did in your notebook, but I'm going to write something which is almost the same thing like what you have in your notebook. Maybe you can just focus on what is written in your notebook. So let us write the definition of isolated singularity and definition of their classifications. So an isolated singularity of a function f is a point z0. We are in complex analysis in C a set of complex number such that f is analytic. So f analytic here means that as f had made a Lorentz expansion. So it is like their expansion in a puncture neighborhood. So it's like a closed neighborhood. Like this. But not analytic. At the not. So it is like when you want to look for singularities, you just have to look maybe uh, the different points at which f is not analytic. And you also have to show to ensure that it is a close neighborhood or something like that. Now, given a Lorentz expansion, so it looks like the Taylor expansion, but it is more general. Here we even have negative, so integer. This nice. The singularity is classified as follows. So the singularity is classified as follows. So a singularity is said to be removable if an is equal to 0 for all n less than 0. The singularity is a pole of order m if a minus m is different to 0 and an is equal to 0 for all n less than minus m. So the singularity is essential. It's essential if infinitely many negative coefficients are non-zero. And also to give another thing, the residual at a singularity point is the coefficient minus 1. What next? So the next question is to find singularities. Next question. So this one was just basic definition that you know well. So let us find isolated singularity. Classify them and compute residues. So this is our f functions. Exponential of 1 over z minus 1 over z plus z minus 2 over z cubed plus 8. So this is our function. So what we are going to do here is to slip this function into two functions. So it can be slipped. So we take this one like f1 of z, f2 of z. So we are going to first looking at the singularity of f1 of z. So to see the singularity, you have to see where you have a problem. And you notice that when you have a problem with this function, when you are computing maybe the image of f1 for z equal to 0. So the only singularity, the only problematic point is z equal to 0. So because of the term 1 over z and the denominator. So use the expansion of this. So by using the expansions of this, so it is equal to the summation from this. So this is something that we know. It is well known. So the Taylor expansion of the exponential function. Hence, now if you remove the term, so if you remove 1, so 1 is the term and at n equal to 0. So this summation is going to go from 1 to infinity. Because at n equal to 0, in the right hand side we have 1, and if you send it on the left hand side, it becomes minus 1. And the right hand side, the summation there, we start from 0 to, we go from 0 to infinity. Now we have to divide this term by z. When you divide this term by z, what do you have? You have this. When you divide it by z, and this gives something like, so if you replace by 1, so you put n by 1, you have this. By 2, You have 2 factorial z3, 3 factorial z4, and so on. So this is this Lorentz series. This Lorentz series has infinitely many negative powers. So we can conclude that z equal to 0, it is an essential singularity. Of this. And you are going to see that this one, it doesn't have any impact to the second one. So to the second function here, if you place z by 0, it doesn't have any impact. So it's not a singularity there. So it means that the singularity of f1 is going to be the singularity of all the function f. Even here, you're going to notice that the singularity of f2 is not going to have, so the singularities are not going to have any impact on f1. So it means that the singularity for a function f2, there will be the singularity for the whole function f. Now, also, the residue um, so this one is related to this. Just a precision. So the residual at 0 is the coefficient of this when you have an essential uh, singularity. Also, the residual at 0 is the coefficient of 1 over z. But we are going to notice something. If you see this series, if you see this series, it start at 1 over z square, 1 over z. After 1 over z square, we have 1 over z cube, 1 over z power 4. But we don't have 1 over z. So if you don't have 1 over z, it means that the coefficient in front of 1 over z is 0. But in the series above, the powers, you can see the powers. So you have z negative 2, z negative 3, z negative 4, etc. And there is no z negative 1 then. Therefore, that coefficient is 0. So it means that has the residue of has z equal to 0, it is an essential singularity. And we know that for an essential singularity, the residue is the coefficient a minus 1. It means that, and this coefficient is 0 because the coefficient a minus 1 should be the coefficient of z negative 1 or 1 over z. Now, singularity of this one. Basically, you know that when we are looking for the singularity, we are looking for the solution of the denominator. So what you just have to know to do is, you know that z cubed plus 8. If you factorize this, what are you going to have? So it's going to be z minus 2 times a polynomial of degree 2. So this one, it is az squared plus bz plus c. But I can remove this. I can remove this a because I know that a is 1, since that we have z cubed. So we can just look at a and b. So we have z cubed here plus az squared plus bz minus 2z squared minus 2az minus 2b. So we take terms. So we have here a minus 2 z squared plus b minus 2az minus 2b. So if we identify this, so we have a minus 2. We don't have you don't have a z square here. On the left hand side, we don't have a z square. So it means that this coefficient is equal to 0. We don't have also a z. So this one equal to 0. And you have a constant which is equal to 8. So finally, a is equal to 2 and b is equal to minus 4. So finally, is equal to this plus z squared plus 2z minus 4. Is it true? I think, is it true? What do we have there? Do we have, okay, nice. Maybe people are asking why I decided I put minus 2 here, because the trivial solution of this is minus 2. This one is a trivial solution. So it means that if you want to factorize this quantity, if you want to factorize the denominator, because we are looking for the solutions, we are looking for the singularities. So if you are looking for the singularities, it means that you are looking for the solution of the denominator, so the root of the denominator. So that is why you have to firstly factorize this term in a denominator, and the easiest solution here, the easiest root here is negative 2. And you know that this one is a polynomial of degree t. So if you have negative 2, so you have z minus 2, which is a polynomial of degree 1. So it remains to find a polynomial of degree 2. So this polynomial of degree 2 is just this quadratic polynomial. And you just have to look for a coefficient. So now this one, if you take it equal to 0, so we have z equal to 2, as we know. Equal to 0. Now, if you compute the discriminant here, you need to solve this. So it is 4 here. I hope that I'm I'm everything is clear. What I did is clear. Oh, it's plus here. It is plus here because the root is minus 2. The root is minus 2. So to have minus 2 has root, You have to put plus 2 here. So to modify this, no, it's just like people are sleeping. I don't know why you are sleeping. I don't know if you just want to copy the final answer. I don't know what you want. I hope that you are understanding. If not, it is very bad. So Z1 is 1 minus square root of Z2. So these are the three singularities. So Z equal to negative. So Z equal to 1 plus I, Z equal to I minus 1 minus I squared of 3. Uh, Now, what is the in which class those singularity belong? So since since this root, so the root of the denominator are distant, each gives a simple pole. So those the singularities to write again the same thing that we previously wrote are and each is a simple pole. Now the question is to see or to know how to compute the residues at the pole. So I know that you have the formula. So we are just going to apply the formula that you have. So residues at the poles of F2. Maybe I'm going to do it in another way, but and you can also use this way. You are going to find the same thing. We know that for a simple pole, Z naught of this quotient. So you have this quotient with Q Z naught equal to 0 and Q prime Z naught different to 0. This is the residues. The residues is PZ divided by q prime of z naught. And that is what we are going to apply here. That is what we are going to do for the three different. So for z equal to -2, for z equal to 1 plus I squared of 3, for z equal to y minus I squared of 3. In fact,
Please,
z,
can you go over that side?
where?
The residue, no, just this one. The residue at the pole, P of Z over Q of Z. Like, is the
Yeah.
formula always like this? For instance, if you have P of Z over Q of Z and you want the residue, will
Yes,
it
so
always be P of Z naught over Q prime of Z naught?
exactly. So when this condition, so when you have these conditions satisfied, so when you have q of z naught equal to 0 and q prime of z naught different to 0, then the residues is going to be equal to this. So you have to make
Okay,
sure.
thank you.
Nice. Now, what do we know? We know that our P is z minus 2. Our Q is this one. So the derivative is, so the derivative is 3z squared. So meaning that the residues of this function, which is still the residuals. So the residues of f2 is the residue of the function f, because it doesn't have this singularity z naught doesn't have any impact on f1. So it is equal to z naught minus 2, p of z naught. So p of z naught, which is z naught minus 2 over the derivative. So this is the formula that we are going to apply for the three singularities, to the triple. So residue at z naught equal to -2. You just have to replace. So it's going to give you -4/12, and you simplify, you have -1/3. So I see that this one equal to this because there is no contribution from the first term to the from f1. Now residuals. So to do this, you have to compute z naught square based off that formula. So the formula is z naught minus 2 divided by 3 z naught square. You have to do it like that. Now what is z naught minus 2? You So this is then equal to There's a 3 somewhere. So you can see that you can simplify it. What is down there is twice what is up. So what is down there, it is like this. The residual here is the same thing because they are conjugate. So by symmetry. Okay, last exercise. We are all tired. Exercise 5. So the first question, given a functions f in L1 of R. So let us write the Fourier, this was the definition of the Fourier transform This one is the Fourier transform of f and proof that so the proof that the Fourier transform is in L1 of is in L infinity, sorry. Now I don't know which definition of Fourier transform was given. We are going to use the definition of the Fourier transform that we know. So I'm going to write the two different expression, and you are going to choose what you know. So you can also write it like this. So what is the one that you know or that was given during the lecture or what you have in your script? Is it the first one or the second one? Because they are the same, but depending on what the lecturer said. So it's better to use the one that the lecturer gave during the lecture.
I
Or
think the first one.
the
I think
one.
the first formula. The first formula.
Okay, the first formula. Nice. So let us use the first formula. So the first formula. So let's show that the Fourier transform is in this. So the hypothesis is that we know that f itself is in L1. Now, for every k in R, what do you have? If you take the absolute value of this quantity, if you take the absolute value of this, and this is less than absolute value of S, or the modulus, it's better to say the modulus because we are in C. We are using complex number. Listen. Yeah, in R, but it's better to say modulus. You know that the modulus of exponential is 1. This is 1 known. So we just remain with this. And this is what? This is the L1 norm, as you know. This one is just the L1 norm. Maybe I'm going to say the L1 norm square. 1.
Sorry, can I ask a question?
Yeah.
Why is the absolute value of exponential ikx
Mm.
equals to 1?
Oh, okay. This is the modulus of, in fact, this one is equal to this. So there's no
You
square
say?
here. No, I'm coming. There's no any square here because I'm going to record two things. Let me record something. So exponential of this is equal to cosine of this plus I sine of this, right? So the modulus of this, it is the square root of cosine square plus sine square, right? Cos square plus sine square is 1. Albert is good. The modulus of A plus IB equal to square root of, is it okay?
Yes, yes, thank you.
Okay. So I hope that you understood also why this integral is the L1 norm.
Yes.
In fact, this one is the LP norm of F. The LP norm of F is this one, the case where P is finite, of course, is the integral of, one over P. So it means that if P equal to 1 has here, you're going to have, if P equal to 1, you're going to have this, what is written here. So P equal to 1, it will be the L1 norm. And we mentioned that F is L1, so everything is good. And F belongs to LP. It means that F is measurable and the LP norm is finite. That is the meaning of being in LP. So your LP norm is finite. Now coming back to our main purpose, we have then the norm, the modulus less than the L1 norm of this. So if we take the supremum over k, this is for all k. Taking the supremum of this over k, so if we take the supremum on the left hand side, we are going to have the L infinity now. Maybe this norm is less than, it's finite because in the beginning, in the hypothesis, it was mentioned that f is L1. So f is L1, that is why this one is finite. So the last question of this session, and the last question of today, using the Fourier transform, let us solve this PDE, this ODS. So this ordinary differential equation, y prime prime plus y prime prime of x plus yx equal to, so this. So you know that to do this, you just have to take the Fourier transform in both sides. So it is like you have to take the Fourier transform in both sides. So the Fourier transform of this equal to the Fourier transform of this. Or instead of using this expression, you can just put the hat. I can call this one J. So to avoid complication. Now there is something that you have to know. There is a relation between the derivative, the Fourier transform of the derivative and the Fourier transform of the initial function. So this one is equal to what? So this one is equal to minus k squared. That is it. In fact, if you want to have more understanding, it is like this. If this one was power p, it is going to be like this. So if we were using maybe the derivative of order p, so it's going to be like this. So that is why when p equal to 2, you just replace p by 2 here. You have I squared, which is minus 1. You have k, which is k squared. I hope that you understood. So this is a very simple formula. And you also have to know that this Fourier transform is just going to give a particular solution of this OG. So by the end of the day, to have the final answer, we are going to find the homogeneous solution of this OG. So the homogeneous solution it means that we are going to take the principal part, solve it equal to 0. So it means that the right hand side is going to be set equal to 0. So we have this. If you replace here, you are going to have 1 minus k squared Fourier transform of this equal to this. Now, what is the Fourier transform of exponential minus absolute value of s? So let us compute it. So this one is the integral from minus this to gx exponential minus kx dx. So what we know is that you have the absolute value. So we know that when x is negative, the absolute value of x is minus x. So we are going to have exponential x here. When x is positive, the absolute value of x is x. So we are going to have minus x here. Because of that, because of,
Oh,
yeah,
it's why didn't you bring the 1 over root 2 pi when you were writing the G cap?
when I'm writing what?
The Fourier transform, we know that the formula is 1 over root 2 pi integral minus infinity positive infinity
Yeah,
e to the power blah blah something. But when you were writing the Fourier transform for the G, talking about the last one, you didn't bring the 1 over 2.
let me start here. So I understand what you mean, but that case is the case that when you want to normalize everything.
Oh, okay.
Okay, nice. Now here you have exponential y minus this exponential so the computer going to have this plus this, so which is equal to 2. Now is it 2? Yeah. Oh, I forgot to change the pen. Okay, now taking back coming back here. So we have this. And from this we have this one. You can do a decomposition. So this one is the Fourier transform of y. And you know that to have y now, you have to apply the Fourier inverse. So the inverse transform. Actually, these things are well known, but I can give you the formula of the inverse transform. So the inverse transform, yeah, it is so the integral you just have to put the Fourier transform exponential of, you remove the minus dk. This is how we compute the inverse transform, or the inverse of the Fourier transform. So if you come here, you put this thing, you compute this, what you are going to have. So you apply this. Now we have for 1 over 1 minus k square, it is well known, it is square. Yeah, it is very difficult if you don't know it in your head. And for these guys, it is half of exponential. So you should know this. So this is just a particular solution. Now, homogeneous solutions. For a homogeneous solution, you just have to solve.
Hello.
Yeah.
This concern the one that you wrote with the green pen.
Yeah.
Is it the k or the x?
Dk.
Okay.
You have to integrate over k to get the final answer in terms of x. Now, you know that to find this thing, you use the characteristic equation. So you have r squared plus 1 equal to 0, have r squared equal to minus 1, which is equal to plus or minus, so which is equal to I squared. So r equal to plus or minus I. Then the homogeneous solutions is just a cosine x plus b sine x. A, b in R. So it means that the final solution is the homogeneous solutions plus the particular solutions. So I think that everything is finished here. So this one was the last question of the subject. Maybe you have any question, you can let me know. Otherwise, if you don't have any question, we are going to, if you don't have any question, we are going to stop it. So we are going to close the session here, and or to stop everything. And as this one was recording, we are going to put it on the website. I'm going to share the link with you, so I'm going to put it on my personal YouTube page.
I have a question.
Yeah.
So do we use the Fourier transform to find a particular solution only?
Yes.
Okay.
Thank you so much. Can we get the PDF of the
Of
notes?
course, of course, of course. I'm going to share everything with you.
Okay, thank you. Let's see.
I don't know if what's the guy's name. If the guys was there, the guys who contacted me, I don't even know
Yes,
them.
yeah, I'm here.
Ah, okay. I was thinking that you were not there.
No, 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 I'm here. Thank you so much. Mhm.
Nice. Oliver left, right? Oliver is no longer there. Okay.
Please, I can't see the shared PDF. Was it on the platform or you sent it to him personally?
This PDF,
Yes, please.
yeah, I'm going to share it.
Okay, thank you.
Okay, you're welcome. So I'm going to stop the session.